Afternoon, everybody, and welcome to our webinar this afternoon on single-use sterile disposable items and their sterilisation and acceptance criteria. Before we get started, just a few housekeeping pieces. If you have any technical issues, please pop a short message in the questions box on the right-hand side of your screen. And during the webinar, we would invite you to ask questions also using that same questions box. At the end of the webinar, time permitting, we'll try to answer as many of those questions as possible. Any we don't get round to, we will answer offline and share them with you along with the slides. So, as I said, good afternoon and welcome to this webinar, the single-use sterile disposable items, sterilisation and acceptance criteria. Oh, this slide's decided not to move. Just give me a second. Oh, there we go. Technical issues for me already. So my name's Annette Russell and I'm the sterile and non-sterile microbiology lead at RSSL. I've worked in the commercial team here for over 7 years and my role is to support our clients with a wide variety of microbiological testing, from routine microbial limit testing to more complex environmental monitoring support or cleaning validation projects. My details are on the slide now if you need to get in contact with me. Oops, gone the wrong way. For those of you that are new to RSSL, who are we? Well, we're a growing CRO supporting clients in a wide variety of analytical services. We've been around for over 30 years and are based exclusively in the Reading area, where we have 4 separate sites. For those of you that don't know where Reading is, we're about 40 minutes out of London and Heathrow. Our 4 sites accommodate over 250 scientists working and supporting clients in 12 different technical areas, of which microbiology is just one of them. We support clients globally, and we have clients from all around Europe, as well as from USA and as far away as Singapore and Australia. RSSL is a trusted CRO with a big emphasis on quality, science and service, and this can be shown by our high Net Promoter Score. Because our sites sit close to one another, we can show great agility to manage complex multidisciplinary projects. We have a dedicated multi-lab project manager and a client liaison managers who can ensure these complex projects are kept on track and managed throughout their lifetime. You may not be aware, but we are backed by the multi-billion-dollar parent company Mondelez, allowing us to have access to funding support to support our expansion and growth as our markets grow and diverge. In the wrong way. So how can we support your sterile manufacturing? So we help to support the Annex 1 regulations and are lucky to have a knowledgeable technical team who can advise and support you on this. We can do raw material testing, investigative support, and we can support any issues you may face, such as impurities or foreign particles in your process. We have a well-equipped and extensive microscopy department which can help build a specific particle database for you and for your manufacturing processes. And microbiological support can also help with microbial identifications, such as EM isolates or any positives you may get in your bioburden analysis using our state-of-the-art MALDI-TOF. We also help with sterility assurance, and we have a extensive extractable and leachables team that may be of interest if you are using single-use plastics in your process. So that's enough of me now. Let's introduce you to our speaker today. I'm sure many of you have heard and seen Dr. Tim Sandell's many publications. Tim has over 25 years experience of microbiological research and biopharmaceutical processing. Tim is a member of several editorial boards and has written over 600 book chapters, peer-reviewed papers and technical articles relating to microbiology. Tim works for a pharmaceutical manufacturer in the UK and also finds time to be a visiting tutor at both the University of Manchester and the UCL. So I will now hand you over to Tim for the bulk of our webinar.
Okay, thank you very much, Annette.
Can we? You're in. That's it. Thank you.
Yeah, okay. The power of the computer world. Okay, right. Thank you very much. And yes, great pleasure to be back with you again. So, as Annette said, this presentation's looking at single-use, sterile, disposable technologies. So we're going to begin the webinar by looking at some of the different types of single-use items, and then we'll be moving to look at different sterilisation technologies, some of the issues around shelf life, some of the things that can sometimes go wrong in terms of things like discoloration and embrittlement. We'll also be looking at, for those single-use technologies that come into direct contact with product, how we might evaluate the sterile path, and one of those options is microbial immersion studies. And we'll also be looking at the risk of introducing toxic substances into the product. So this is the area of leachable and extractables testing. And we'll also be considering some of the factors that we need to weigh up if we are seeking to undertake a change control or approve a new vendor or adopt a new item into the manufacturing process. But to begin with, we'll just recap on what we mean by these types of technologies. So single-use sterile disposable technologies refer to any item of biopharmaceutical equipment that is, one, sterile, and two, intended only to be used once before it's disposed of. And for the most part, these technologies are meant to be utilized in the same way as their reusable counterpart. So if we were using a stainless steel vessel, we might be substituting that for some form of bag-based technology that we would then dispose of at the end of the operation. And the fact that these items can be mixed and matched and replaced is something that can improve their flexibility, and it can also, at least potentially, lower operating costs. And these technologies are generally manufactured from plastic polymers, and this is a process of typically by injection molding, extruding, and then blow molding. Although with the advent of some 3D printing technology, then there are other aspects of additive manufacturing that can sometimes be brought into the process. And they would be assembled within a grade A environment and then subject to a method of sterilisation. And we'll be looking at some of those methods shortly. So the first wave of single-use systems for biopharmaceutical, biotechnological and mainstream pharma applications really originated with cell culture and finding solutions for processing cell culture media, and then areas like buffers, and then extending out into all forms of the workflow. So we have technologies like tubing, capsule filters, single-use ion exchange, membrane chromatography devices, single-use mixers, bioreactors, product holding bags, with or without the ability to mix, sterile fluid containment bags, aseptic connection devices, sampling bags, so for taking bioburden samples, and also some of the sampling receptacles as well. So the advantages, and I've alluded to some of these, but they're areas like the ability to reduce processing time. And this is through the removal of the necessity to clean and to recycle equipment. So the stainless steel vessel would need to be subject to a validated cleaning cycle, a validated drying cycle, and then some form of sterilisation, most probably autoclaving. All of those steps are removed. Another is to reduce manufacturing costs, as I mentioned, and this very much depends upon the trade-off of buying the particular items against the cost of running the utilities and also the cost of any change. But there's the potential for these items to be more reliable, flexible, and cost-effective. Another reason is seeking improved sterility assurance. So often processes like gamma radiation might be more effective than particularly difficult to autoclave items where there might be the result of wet loads, for example. There can also be improvements to controls to reduce batch rejection. And then many of these items will come barcoded with clear identifiers, so we have the ability either to undertake lot control or even lot tracking, depending upon our application. There are some other advantages. So we've mentioned.
Hi, sorry to interrupt. Just your GoToWebinar dashboard is on the screen. If you just move it over to a second screen.
Ah, sorry.
Thank you. Perfect. Thank you.
Okay, is it gone?
Yeah, it's gone. Thank you.
Okay, that's great. So you can tell this is live as we go through it. Yeah, we've mentioned eliminating the need for cleaning. We've said about reducing cleaning steps, but coming out of cleaning steps is also reducing the number of chemicals that we use. And every time we use particularly cleaning chemicals, disinfectants in the process, these have to be disposed of. There's going to be certain environmental regulations relating to those. There's obviously the removal to perform in-house sterilisation and the costs involved in operating an autoclave. There's the advantages of storage requirements. So often these items take up less space, and if there's an appropriate relationship with the supplier, then it's potential to adopt sort of just-in-time usage. And in with inventory control, lowering process downtime, increasing process flexibility. And again, through the removing of the need for, say, cleaning validation and the subsequent storage, we're taking out some of the risks of cross-contamination. However, the world is not that simple. So we do have some disadvantages as well. So some of these disadvantages, and some of these are called out within EU GMP Annex 1. So we have the interaction between the product and the product contact surface. And this could be absorption of the product. So we might end up with less yield than we anticipated. Or we have where the interaction between the product and the single-use technology can lead to leachables and extractables, and we'll look at the difference between those two shortly. Often these technologies are more fragile, so obviously the robustness of stainless steel is being switched for plastics. There can also be an increased number and complexity of manual operations, depending on how these items are presented. So we might end up doing more connections, for example, and if these are aseptic connections, then that's introducing an element of contamination transfer risk as well. And sometimes the assembly can also be complex for the operator who needs to perform it. So again, rather than one large ready assembled piece of stainless steel, we have numerous pieces of plastic technologies that we need to piece together. There can be complexities if we're buying in pre-sterilized filters with integrity testing, both pre and post use, and how that's going to align with other technologies to enable that to happen. There's the risk of damage or imprecise sealing or connections that don't quite fit together the way they should. So we have the risks of holes or leakage. We have to be mindful that although the items are themselves sterilized, the opening up of the item, particularly the final layer of packaging, is something that can introduce contamination. So we do have a risk of compromising the system at the point of opening. And we also have to be mindful about particle contamination as well. So again, particularly if the sterilization process has imparted anything that could then lead to particles forming and being deposited into the air or into the product. We also need to be careful with the vendor we select. So we'll be looping back at the end to the change process, but when we're embarking on selecting a technology and picking a particular vendor, then we need to be certain that the vendor we are going to go with is reputable and has undertaken the necessary qualification steps. So audit as part of a sort of pre-approval process is very important, as is having knowledge of where the vendor gets all of their components from, what is the sterilization method that the vendor is going to be using, how has the technology been designed, and how easily is that translatable to your particular process. What's the likelihood of non-supply? Do you need to qualify two different technologies in case one vendor is not able to supply, and that brings your process to a halt? And then linking to the sterilization method is, what is the verification of the sterility assurance system, and how can you guarantee that this item that is labeled sterile is actually sterile? So this takes us on to sterilization. So there are different ways by which these items can be sterilized. The conventional way and the longest established method is the use of gamma rays, gamma radiation, and this is an electromagnetic form of radiation, and the gamma is generated using a radionuclide, either cobalt-60 or cesium-137, cobalt being the most common. And gamma radiation is highly effective at destroying microorganisms, provided there's sufficient energy and there's no barrier that's going to obstruct the radiation reaching the microbial cell. And when it does, if you take a bacterium, for example, then gamma radiation is operating at the molecular level, and it's breaking down bacterial DNA, and it also inhibits any form of cell division. So gamma is quite effective, and it's fairly straightforward to achieve sterility assurance level of 10 to the -6 or greater. Gamma is also fairly good at avoiding material degradation. And by degradation, this would be something that we'll return to, but it is an important factor. Is, you know, it might be perfectly feasible to sterilize something, and it may or may not degrade, or there might be degradation over time as we move towards the end of the shelf life. So this, we're talking about changes to the properties of the polymer. So we might see an alteration of tensile strength. We might see a change in color. So some of these processes can render transparent or translucent plastics and turn them sort of yellowish in color. We could get alterations to shape or molecular weight. Now, there are also alternative technologies. So there is ethylene oxide, which is a gas, and this is less common. It was more common in the 1990s and 2000s, but it tends to be shied away from because, one, it's more difficult to get rid of the gas residuals, and also because ethylene oxide is quite a nasty substance. If there are residuals, it's a mutagenic compound. So the other recourse is towards other irradiators. So a beam from an electron generator, or X-rays, and we'll be looking at those shortly. But with a lot of these technologies, and one of the reasons why gamma's always been traditionally leaned towards is because of trying to avoid the impact of heat on these items, because obviously they're made of plastics, and in many cases we're seeking not to damage the mold. So a lot of plastics, particularly polystyrene, for example, are incredibly temperature sensitive. So we need often what's classified as cold sterilization technologies. By cold, that means a small rise in temperature. It's quite difficult to achieve zero rise in temperature, but we're trying to minimize that as much as possible. And there is a standard that governs the sterilization process. And it's a standard for medical devices, but in this sense, the medical device and the single-use sterile disposable system are ostensibly the same, or at least is very similar. So we have this ISO 11137 standard, and there are 4 parts. So part 1 covers the development, validation, and routine control of radiation sterilization process. Part 2 is about the specific methods for determining the minimum dose needed to achieve the specified requirement for sterility. Part 2 also looks at the sterilization dose audit, which is used to demonstrate the continued effectiveness after the validation has been completed to ensure that we have consistency of sterilization. Part 3 is guidance on the way we're measuring the effectiveness of radiation through dosimetry. And part 4 is about ongoing controls. So what we're going to do next is look at some of these sterilization technologies in more detail. So we'll be looking particularly at gamma, E-beam, and X-ray. So we've introduced gamma a little bit, but there's a few more things to get across. So the process of gamma radiation is a form of ionization, and it works through electron disruption. And I mentioned that it's highly energetic, and it's a physical means of sterilisation because the rays pass directly through the item that we're seeking to sterilise, and the electron disruption is a physical alteration to the object. And I mentioned that cobalt-60 is the most common radionuclide that's used, and it's a byproduct of the nuclear industry, where non-radioactive cobalt-59 is transformed into radioactive cobalt-60, and this emits ionization in the form of photons, which then become electron disruptors. The great advantage of gamma is that as soon as the gamma source is removed, so as soon as the radioisotope is plunged back into water and encased in concrete, the radioactivity stops immediately. So there's no ongoing residual issue. So unlike, as you mentioned, with ethylene oxide, there's no lingering effect. It's a cold process, as you mentioned, so there's no significant increase in temperature. The process is not dependent upon the ambient humidity, temperature, or pressure. The most important variable is the strength of the radiation dose, which is expressed as a measurement of how much energy is absorbed and the exposure time. And we're measuring the radiation in units called kilograys. And the sort of standard definition of that is that 1 gray is the absorption of 1 joule of radiation energy by 1 kilogram of matter. So that's gamma. With electron beam, or what's more often referred to as E-beam, this uses high energy electrons to sterilize an object, and like gamma, it's a method of irradiation, and it ionizes the material as it strikes it by stripping electrons from the atoms of the exposed material. And this ionized environment is very damaging to microorganisms, and again, it's disrupting DNA. Generally, E-beam is shorter than gamma radiation, and it's created by using a high energy electron beam accelerator, what's often termed a linear accelerator. And this is a particle accelerator that increases the velocity of negatively charged subatomic particles by subjecting these charged particles to a series of, if you like, oscillating electric potentials, and this takes place along a linear beamline. So in effect, the item that we're seeking to sterilize is showered by accelerated electrons that move over the target, the items we're seeking to sterilize. And these electrons within the linear accelerator are generated from tungsten, and they are highly energetic. Another sort of advantage of the process is that you can simply switch on and switch off the linear accelerator, and that ceases the radioactive effect. So with gamma, you've got to take the radioisotope and protect it in some way that it's no longer able to cause harm to humans. With this device, you just simply flick a switch. In terms of the energy levels, these are expressed as millions of electron volts, which is the expression MeV. and the energy level will fall between 3 and 12 MeV, or millions of electron volts. And a given sterilisation process normally has an accelerator operating at a single energy level. Generally between 5 and 10 million electron volts is sort of fairly standard, and this is quite useful to process slightly thicker products or things that are already pre-packaged. And this can be also suitable for if you have things in, say, corrugated shipper cartons. You can the radioactivity will pass through. And generally, the electrons from the linear accelerators have a usable penetration, and that's expressed in terms of 3 millimeters. If you can imagine the item you're seeking to sterilize, it's the ability to penetrate 3 millimeters in water for each million volts of accelerating potential. So if we go back to 3 MeV, in theory, we could penetrate 9 millimeters of material in water. So if we take that up to the 10 million electron volts, then we can penetrate around 3 to 5 centimeters of material. And then for items that are lower in density, then we can penetrate further, and items that are greater in density, then we would start to get barriers. So in that sense, gamma is more penetrating than E-beam, but E-beam is faster than gamma. So there is a sort of trade-off, and some of the decisions are going to rest on the types of material that we're seeking to sterilize. So moving on to X-rays, and anyone dealing with the change control process may well have noticed that in the last couple of years, there's been a number of manufacturers of these sorts of technologies who are requesting switching from gamma radiation to X-ray. So X-ray is no longer a sort of an alternative or less popular technology. It's increasing in scope. And the reason for this is the cost of gamma radiation has increased because of the scarcity of getting hold of cobalt-60. So things like E-beam and X-ray are being looked at more often. So with X-rays, this is again an electromagnetic form of radiation, and it's the use of energetic photons that can penetrate items and sterilize them. So X-rays have a wavelength in the range of 0.01 to 10 nanometers, and that gives a frequency of between 30 petahertz to 30 exahertz, and energies going from around 100 electron volts to around 100,000 electron volts. And X-rays have the highest penetration capability of all, so they're more penetrative than gamma, and in turn gamma was more penetrative than E-beam. So again, one of the decision points all comes down to what's going on in the materials that we're seeking to sterilize. So X-rays are frequently generated using an X-ray tube, and this is a vacuum tube that uses a high voltage to accelerate electrons that are released by a hot cathode, and these are increasingly taken to their maximum velocity. And at this high velocity, electrons collide with a metal target, and there's a cathode and anode, and it's the anode that then creates the X-rays that are pushed back towards the object. And the same effect is imparted upon the microbial cells, where there's an interaction between the radiation and the cellular DNA. So we've seen this sort of introduction of high power, reliable accelerators, and the ability to sterilize products in their final containers is also another added advantage that the X-ray technology presents. So we have the broadly similar ability to kill microbial cells to gamma, and we have the broadly similar material compatibilities, but that's still a factor we need to look at. And in terms of how we would judge the effectiveness of sterilisation, so it is possible to use biological indicators, and this may be done by facilities as part of initial setup, but it's more common to assess established product practices through an assessment of product bioburden. So it's an understanding of the numbers and types and relative resistance of microorganisms on items pre-sterilisation compared to their verification of their sterility post-sterilisation. So that gives us sterilisation, but as mentioned earlier, there are a number of other factors that need to be considered, and there's a fairly extensive evaluation that needs to take place before a single-use item is adopted. And this will be a combination of evaluations that will be performed by the vendor and by the end user. So we need to consider the biocompatibility of product with the item. We need to understand mechanical properties like tensile strength. So if we have a bag, we don't want that bag to as we fill it to its capacity. With things like filters and tubing, we need to understand their pressure rating before they might rupture or ping off. We may need to understand gas transmission properties when we're talking about bags. We want to know that filters can be correctly integrity tested, and would have concerns about chemical resistance. We'd also need to extend these concerns to embrittlement. So if an item is going to be structurally damaged, and again, as something I said earlier, it could be initially at the first blast of radiation, or this could be something that happens over time. So we're establishing shelf life is quite important. This can be a particular issue because if you have items that have been sterilised and correctly wrapped and they go past their expiry date, then chances are if the packaging is integral, there's not really any factor that's going to alter the sterile status, but the usability of the item might be affected in other ways. Embrittlement is quite a key one. Another one is sort of stiffening and loss of flexibility. So again, one of the advantages of these technologies is they can be bent and twisted and take different combinations of materials. So if they become, if they lose that flexibility, that becomes a problem. There's also another form of aging like post-crystallization, which again can alter the reliability. We mentioned discoloration, which is often this yellowing. That may or may not matter depending on what we're using the item for. But if it's something that is in the final presentation that's going to a customer, then you know, selling something that was one day transparent that then goes kind of a funny yellow color, it's not something that's always going to be popular with the consumer. We can also have hazing, which is again is something that can occur with transparent items. We can have reduced melting points, so we've got lower thermotolerance. That may or may not be an issue. For things like blow-fill seal technology, it can be quite damaging. And we also need to understand whether or not we've got any residuals, and this is a particular issue with ethylene oxide. So the choice of sterilisation method needs to be optimal for the specific item or group of items to be used and sterilised. So it may not even be the case to say, well, we've looked at this particular type of plastic and we know it's okay. It might be okay for one item in one particular combination. It may or may not be okay for another type of item in another type of combination. We also need to understand the likely bioburden on the items that we're seeking to sterilise. And we need to have good oversight of the sterilisation technology, the type of technology, the processing conditions as well, because one thing that Annex 1 emphasises quite strongly is that all outsourced sterilisation need to have the same level of control and oversight as something that is done in-house. Something else to take account of with structural integrity is when items are exposed to extreme conditions. So if we're taking our single-use technologies into, say, a freezer, we would need to understand what happens. And we'd also need to understand what might happen during transportation. If we're having something delivered by lorry from Spain and it breaks down on a hot day, is that going to have any deleterious effect to the items? And this can be particularly important when it comes to sterile connection devices as well, because if these have any leakage, this could be problematic. Another consideration is, particularly with tubing and connectors, is the avoidance of microbial ingress, because if we're reliant upon these technologies to guarantee a sterile product path, then we need to have data that's going to support that. So we can either have integrity testing, microbial testing, or a combination thereof. So with a lot of aseptic connector devices, often these are immersed in a microbial soup, and then something like a microbial culture medium is pushed down through the device and then evaluated with the requirement that the broth does not detect any contamination. There's always a weakness with these methods because they are probabilistic and they are highly dependent upon the test conditions. But this sort of combination of integrity and microbial testing can be very useful, particularly when we're making, say, aseptically filled products, and we're very reliant upon these technologies to maintain sterility when they're connected together. Okay, so I mentioned leachables and extractables earlier, that they are similar but slightly different terms. So leachables are those impurities that could leach from our plastic material when the drug substance or drug product comes into contact with it. So this is what's referred to as compound migration. And an evaluation of leachables will give us information about the actual compound migration that may occur. With extractables, this is subjecting, again, the single-use item in contact with the product to harsh conditions. So what happens if the temperature gets elevated, the pressure goes higher, etc., etc. So these are the potential for compound migration. So there is a slight difference there, but both are important to evaluate. So leachables and extractables can be present if we're using inferior materials. So if we're not going to a reputable supplier who's using well-proven plastics, then we can have a problem. We can also have problems if there's a lack of control of the additives or agents introduced to the raw material, if the manufacturing techniques are not robust and reproducible every time, or there's a property of a particular type of sterilisation that alters the material. This is where I was saying if you're switching from gamma to X-ray or to E-beam, then this might increase the risk of leachables occurring. So we do need to perform toxicity studies wherever we are having the product in contact with our single-use item. And this will include physicochemical testing. So we're trying to measure the likelihood of impurities that can be extracted from plastics when they're leached using our extraction medium. So not only are we going to be using product, we also might need to replicate that with something like isopropyl alcohol or purified water over a specified period at a set temperature. And then we'd be measuring for a whole range of impurities. So this could be heavy metals like lead, zinc, tin, and so on. It could be an alteration to acid or alkalinity. It could be the release of organic or inorganic residues. So there's all sorts of things that can come out. And we also have to have an understanding of what's an acceptable level and what is the impact upon the patient in relation to toxicity. And we should always carry out this testing after the item has been subject to our chosen sterilisation method. And we should also have an understanding of the same testing at the end of the shelf life under our selected storage conditions, because we can get these gradual deteriorations over time, and that's going to be dependent upon the external environment. In terms of sort of general tests for the presence of these impurities, then common techniques include things like solid phase micro extraction and gas chromatography systems. So we need to have an understanding that the analytical method that we're selecting is also suitable to give us that basis to proceed to our toxicity testing. There are some other things we need to take into account. So one is receipt. So on receiving single-use sterile disposable items, we need to have verification of sterility, verification of the exposure time. We need to have an understanding of the storage conditions, and then this ability of lot control and lot tracking, and also to do a visual inspection of the item. So there's lots of things to weigh up, and this makes the change control process quite important. So if we're introducing a new item, or if we are changing part of the material or design, or we're altering the sterilisation method, and particularly with all of those where there is product contact, we need to take everything through change control. And for our change control evaluation, we need to have an understanding of the stability and compatibility of the materials, an understanding of the container or package integrity. We need to know what our pre-sterilisation buy burden is, and the confidence that our sterilisation method can effectively deal with that, and what our control parameters are going to be. So we need to have an understanding or discussion with the vendor and agreeing what are the appropriate sterilisation process parameters that will, one, kill microorganisms, and two, preserve the inherent properties of the materials. We also need to be able to demonstrate to ourselves that the sterilisation process and the equipment are capable of operating within these selected parameters. We also want to scrutinise the manufacturer's sterilisation qualification data, whether they've used biological indicators or some other form of dose assessment or bioburden assessment, and also have an understanding that we can keep those levels in control at all times. Another factor that shouldn't be overlooked is, it's all well and good sterilising these items, but we also have to consider how we get them into the facility. So unlike the vessel that we're autoclaving, we're not having full control because we'd have our autoclave leading straight out, say, into our aseptic filling area. We can control that. Here we're talking about items that would need to be probably at least triple wrapped so that we can transfer them into the facility, remove layers at set points, particularly when moving through clean rooms of different grades, and undertake appropriate sporicidal disinfection. So we need to work on that as part of our contamination control and risk strategy, because what we want to avoid is going to all the trouble of coming up with very well-designed items and very robust sterilisation systems and then messing that up by introducing contamination or creating conditions where we've got cross-contamination. Okay, so this brings the main part of the webinar to an end. So what we've done is looked in general at single-use sterile disposable items and some of the advantages like improved sterility assurance, flexibility for the process, potentially lowering costs, but also looked at many of the factors that we do need to consider. So product compatibility, particularly our concern with leachables and the potential for these to be damaging to human health, embrittlement, discolouration, and other forms of damage, and how all of this is really dependent upon, one, the material, and two, the sterilisation process. So thank you very much, and I'll pass you back to Annette.
Thank you, Tim. So just give me a second and I'll get my screen up. So we've had a couple of questions come through. I've got one from Adam saying, do regulators encourage single-use technology?
Yes, I think that's quite implicit within EU GMP Annex 1. So there is an encouragement to adopt the best forms of technology that are available, and many of these single-use things have that advantage. But equally, there are various warnings as well about the different factors and things to watch out for. So it is really important that, yes, it's encouraged, but two, we have to tick all the things off on the list.
Then I have one from John saying, why do companies tend not to use ethylene oxide for sterilisation?
I think because it's quite nasty in terms of the residual. It also takes a little bit longer, and it can, although it's also still a cold process, it can lead to an element of temperature increase, and you just got to be quite sure you can get all the residuals out. So that there was a case of, probably going back quite a few years now, but it was the canisters that are used for the sterility test, and these were there's one brand that was being sterilised by ethylene oxide, and it was found that there was residuals of ethylene oxide still inside, so it gave the potential to lead to false negatives in the sterility test. And nowadays most of them are sterilised by gamma, but it's just another example of the difficulty in driving that residue out.
And then I have a question from, apologies, they're coming through quick and fast now. A question from Svetlana. He says, is it enough to have a risk assessment based on information from the manufacturer of SUS, extractable for acids, etc., leachables with water, or study of toxicity is needed for each product?
It's probably each product, but it does depend, I suppose, on what the product families are. You know, you might be able to look at the products and find worst case ones in particular. But I think if this is something that is going into a patient, then I think you need to understand what those particular product characteristics are and how they're likely to be related when they interact with the particular material. Now, if the product's like, say, has a factor that's not suitable, then of course you can use placebos. But I think a lot of this work needs to be done with the actual product.
The last question from Suresh says, you mentioned that high bioburden can't be justified with sterilisation process capability. Is there any guidance value for pre-bioburden limit?
There are different things in literature, and really, and it does depend on also the types of microorganisms and their inherent resistance, and also the size of the object that you're seeking to sterilise. So with anything in microbiology, there's always ifs, buts, and maybes. But generally, between 100 and 1,000 is normally the peak, because the problem is you might find you've got organisms that only have a certain level of resistance, but if they start layering on top of each other, or they're going to be obscured by something, then the absolute numbers also become a factor, as well as the innate resistance of the individual organisms as well.
Okay, well, thank you, Tim. That's all we've got time for today. I don't know what's happened there. Sorry, apologies for that. So this doesn't want to play with me today. So as I mentioned, this is our last webinar of this series for this year. Look out for our details for webinars in the coming new year, and I will just go back to my details. If you have any questions regarding anything to do with the webinar, or any of the information that we can help you with in terms of extractables and leachables, as I mentioned, or microbial support for Annex 1, please do contact me. The questions we didn't get round to asking today on the webinar, I will forward them to to Tim, and get Tim to answer them for you. And we will send out a copy of these slides along with those answered questions in the next couple of weeks. So thank you again for attending today, and we look forward to seeing you in the new year. Thank you.
Thank you.